Good evening, everyone. Welcome to the Fort Worth Astronomical Society's 2021 presentation for International Asteroid Day. My name is Chris Widmanstätten. I'm a member of the Fort Worth Astronomical Society, and I've been doing these videos for a while now, last year. Today we're going to be talking about asteroids, about meteorites specifically, for Asteroid Day. So I will be going over a little bit about asteroids, but mostly talking about meteorites themselves, because most of the meteorites that we have actually come from asteroids, and they actually tell us quite a bit about asteroids. Excuse me. A couple weeks ago, I did a presentation specifically about asteroids and meteorites. And then we went over and talked about specific meteorites, did some close-ups, some microscope views of some slices, just to be able to show what meteorites are, what they look like, what to expect. Today we're going to do sort of the same. We're going to go into a lot more meteorites, talk about the differences, talk about different types, and specifically we're going to go over some interesting meteorites called the HED group, head group. These are meteorites that come specifically from the asteroid for Vesta, and how we know that these meteorites come from a particular asteroid. So, let's see. You have a presentation, but I don't think we're going to go ahead and use a presentation, because you can always take a look at the video that we have before. Sorry, I'm still fighting off upper respiratory infection, and so I'll be drinking a bit as I can. Hello.
Hello, everybody. I'll be presenting you about meteorites.
I have someone who's almost ready for bed, so he will be going to bed and watching.
Yes.
Okay, he'll be watching and
in my grandma's bed.
very well. And we'll be going over the meteorites now and talking about them, right? Okay. So.
I miss ancient space.
Okay. Are you ready? Are you ready to go to bed?
No.
No? Okay.
No.
Well, I need
Can
you.
I use this magnifying glass?
Yes, you can. I need you to go ahead and get ready so that I can continue. Okay? Ready? Good night. Good night.
Ooh, wow.
All right. Oh. Oh, I knew I forgot. I'm going to go ahead and bring up this presentation so we can go over it very, very quickly, and we can see kind of what this looks like. All right, here we go. Let's see.
Yes, that's true.
Good question. Let's see. What do I have? No, that's not it. That's not it. There we go. Let's see if this has the right view. 100% positive. Oops, definitely not it. No, that's definitely not it. Let's go back to the view. We have the wrong view on here, but that is quite okay. Let's see just how well. Oh, it's always technical issues, isn't it? We're going to try it once more. Nope, that will not do. See, we can see how well this is going to work. And more. Always technical issues, isn't it? Let's try how well this works. Oh, this is not going to work either. Well, this will be fun. Sorry about that. I'd done this before on a different screen. It looked like it was working, but apparently it won't work terribly well right now. That's fine. We'll go ahead, deal with it as best we can. In the meantime, let's go ahead and talk about meteorites. So what are meteorites? Meteorites are rocks that have hit the ground coming from space. So we have, excuse me, we have meteoroids, we have meteors, and we have meteorites. So meteor is, well, let's go with the first one, meteoroid. Meteoroid is any general bit of space degree that's less than a meters wide that's floating out in space. If it hits our atmosphere and starts glowing, it is a meteor. As long as it's glowing, it is a meteor. soon as it hits the ground, it's a meteorite. So any rock that hits the ground, we call that a meteorite. While it's up in the air, it's a meteor. So any particular rock, the shortest part of its lifespan is when it is a meteor. Longest part, meteoroid. And then it hits the ground and it's a meteorite. Anything larger than 1 meter in diameter, we call an asteroid. So I have with me a number of rocks. So let's show off the first one. So this is a meteorite. This is an uncut one. This is a hole. This is roughly what it looks like when it's when it hits the ground. We're going to switch over to here. Let's see how well this will work. I'm going to go. Right. So right now I have one. There we go. One meteorite. So you can see that this is a fairly dark one. Bump up how much light I've got on this thing. Hoping this is good view. Let's see. So this is a meteorite. This is a fairly dark rock. If I rotate it, you can see it is very shiny on the outside. It's the shininess. I'm going to try one more thing. Oops. Let's see if I can get this. There we go. I'm going to get this thing a little bit brighter of an image. There we go, because what I want to do is show off just what the color is. And the color is more of a brown. It's not really black. It's a very, very dark brown. But it's a pretty color. I think it's a pretty color, at least. Let's just take a look what the outside looks like. This is going to be your standard. Whoops. This is going to be your standard meteorite, pretty much. If there are any audio issues, let me know in the chat. I will be watching it. So let me know what it sounds like. We'll see what that looks, what that's like. A number of meteorites that are fairly similar, and these are all different rocks, but they're all similar colors. And oh dear. Oh dear. Now I'm looking for something in specific, and I'm looking for my. I'm looking for a magnet, and I don't see where my magnet went. I had magnets, and a little particular somebody I know grabbed my magnets. Can't find where they are. I had them. I don't have them. In terms of scale, I have a 1 centimeter cube. Kind of tells you just how big these are. They're not terribly large, but they are rather heavy for their size. For example, this one right here is, I believe, 180 something grams, 183 grams. So they are much heavier than Earth rocks. We'll see how that goes. So apparently the focus is not great on these. Let's see if I can fix this. So yeah, let me know in the chat the video quality. There's issues with the video, issues with there we go. This might actually be a little bit better. Issues with the video, issues with the audio, and I will do my best to fix them as I can. Uh-oh, there's no voice. Should be a voice. There we go. So if you hear me, yeah, let me know in the chat if there are any audio issues or whatnot. Okay. So I think this focus is about as good as I can get on here. See how it goes. Okay. I'm trying to do multiple things at once, so it's not always terribly easy to do. That's all right. Let's see how this goes. Excuse me. So I had issues before. We'll deal with it. What we're looking at right now on the outside, this brown coloring, this is called the fusion crust. Fusion crust is what's left over when something when the object is passing through the atmosphere and the heat of it passing through, that will I'm terribly sorry. I'm trying to get everything done as best I can. I keep getting interrupted. As a rock passes through the atmosphere, it goes from anywhere from 11 kilometers a second to 72 kilometers a second through space, and that's its impact speed upon the atmosphere. And it depends on a lot of things, a lot of orientation. Is it hitting the Earth directly? Is it going around from the back? Is it hitting from the side? A lot of factors which contribute to the speed at which it enters the atmosphere. But typically, the faster it goes, the brighter the meteorite's going to be. The meteor is going to be. As it goes through the atmosphere, that heat is the air friction against the rock, and that is ablating away bits of the rock and taking the heat with it. So what's happening is the rock is decreasing in size. Each of these rocks here is about 1/20th of the size of the original rock. 95% of the original rock gets ablated away, and this is all that's left. So if you had something which hits the ground at about a kilogram in size, then the initial one was probably around 20 kilograms, at least on the small scale. For the bigger scale, it scales differently according to size and speed and a bunch of other factors, but typically we say about 95% is ablated in the atmosphere and just turned to dust. So here we have 4 meteorites. Let's see. Now let's just do 5 meteorites. 5 meteorites of various kinds, but they all look roughly the same. And when we're looking for meteorites, this is what we're looking for. We want to see a dark rock sitting on a light-colored surface. And this is why when we go meteorite hunting, we typically go in deserts. So we want to go to some place that has light-colored soils or sands. And when we're looking for them, we want dark rocks that sit on top of the surface that don't fit. We want something that looks out of place. If you saw this rock, actually better yet, let's do this. Let's swap out these rocks. Let's just take one, these two, and this one. So 2 of these are meteorites, and 1 is an earth rock. And you can tell because of the color. You can also tell because of well, let's see. Well, you can usually tell because magnets. If we use a magnet, and I cannot, there's one magnet, but this isn't exactly what I want to use. Let's see how well this works. So we have magnets here, just regular little kitchen magnets. These magnets stick to some of these rocks actually rather well. They do not stick to most earth rocks. The reason is most earth rocks don't have any iron in them. So what we're looking for here is, there we go. What we're looking for here is for a magnet to stick to the rock. For those two, works just fine. For the earth rock, it does not. Now, there are similarities. Smooth. This one's fairly smooth. It's brown, but these are much, much darker. And that surface, that patina, the fusion crust, we cannot replicate this on Earth. And we'll open up a couple of meteorites and show you just why. So if you have any questions, go ahead and put them in the chat. I'll be glancing over and watching in the meantime every once in a while. And again, we'll do the best we can with this. Excuse me, I have to keep drinking water. So these are meteorites that are raw. They're unprocessed. They're basically picked up off the ground, cleaned off a little bit on the outside. But the patina, the fusion crust is intact. And we really don't know what these look like on the inside. They definitely look completely different. They do not look like this on the inside. It's something else. Most meteorites look roughly similar on the outside, where it has this patina on it. The inside could be anything. I have this one we'll put away. All right, so now that we've seen what the outside looks like, we can take a look at what the insides look like. What I have is some slices. Sorry about this. Okay. Let's get these out of the way because I want to be able to show this one. I need to actually be able to flip that. So let's take a look at this video again. Sorry about this. I've got to fix this somehow. Oops. Yep, I'm trying. Something's not quite right here. Let's see how well this works. So this way and flip it around this way. There we go. Northwest Africa, 8327. Northwest Africa, 8327. So NWA. The reason why we say Northwest Africa is a lot of these land somewhere in the Sahara, somewhere in the desert. We typically look for them in Algeria, in Morocco, places where the soil, the ground is this color. It's a very light color, and dark rocks stand out. Well, there's not much out in the Sahara, so nobody really lives out there. Nobody lives out there. People pass through, and so there aren't really any specific places out there except for a few wadi, some oases, and that's about it. So what do? When we name meteorites, we name them according to the place that they land, the nearby geological feature. Well, if there aren't any really named geological features in the Sahara, what do? We just give it the name Northwest Africa. It's generic. So Northwest Africa is the name of this meteorite. Well, actually, Northwest Africa is the location, and then 8327 is just the 8,327th meteorite designated as Northwest Africa. So these can range anywhere from pretty much Morocco all the way across into Egypt. As long as it's out in the middle of nowhere, as long as there aren't really any geological features nearby, it can get that name. So this particular one, see, where was this one found? Let me double check. This one was found in Algeria, 2006. And this is an end piece, so this is cut. If you flip it, you can see the fusion crust here. So the fusion crust is very, very black. Flip it, this is what it looks like on the inside. And what we're going to do, instead of just leaving it like this, we're going to take a good look at what the inside looks like by taking this and putting it under the microscope. Okay, well, this works. All right. So let's look at the edge and get this in focus as well. There we go. Okay, so we're looking at the very edge of this thing right now. You look over, the actual edge. Oh, how does it work? I need something to point with. Let's take a look at this. Out here, the actual edge right there, you can see the fusion crust is very, very, very thin. It's almost like it's painted on. There's just not really anything there. You can actually see We move it a little bit further along. Here we go. So this is a little deposit of iron right there. It's starting to rust out just a little bit. You can see that the fusion crust is right through that deposit. Is just barely there. It does not affect anything on the inside. We can see this one actually has some chondrules on it. So this is a chondrite. Chondrules like these, there, these little droplets, these little round balls. What we think is that these are the solidified remnants of molten pieces of the original um, uh, accretion disk, the cloud from which our solar system formed when the sun was very, very, very young and very, very hot. So eventually these cooled down into these solid little droplets and got incorporated into larger and larger rocks. So these are remnants of the early solar system that we're seeing in these little bitty chondrules. As we go through, I know we've got some somewhere here. There we go. We can see right there, there's a chondrule that's a little bit cut off. See one right there. There's one right there too. Oops, really hard to get it close. There's one right there that's been kind of cut in half. But on the inside, oh, you can see several right there too that are also cut in half. And you can see the fusion crust is just barely there on the outside. So what this means is that it's not burned inside. That burnt part is just the very, very outside, and it is a very, very, very thin layer. It's only a few microns thick. So the heat of passage to the atmosphere never actually gets to the inside of the rock. The heat is all taken away by ablation as little particles fly off of it while it's a meteor. So what we're looking at is an undisturbed inside and a very, very burnt, just a very super thin outer skin. What it also means is when a meteorite hits the ground, there's no fire, there's no smoke coming off of it, not burning, it's not hot, it's not glowing. A meteorite of roughly this size, it hits the ground, it will immediately frost over because the inside is still the temperature of space. The inside does not have time to heat up as it goes through the atmosphere. Hits the ground, it is still, what is it, a couple degrees Kelvin, 10 degrees, 12 degrees, whatever it is. It hits the ground, it frosts over, and it will stay frosted over until it warms up to ambient temperature. So if you happen to see a rock fall out of the sky and it's dark like these rocks and and it's frosted over, that could be a meteorite. Don't touch it. Give it 10-15 minutes to warm up to ambient temperature. And then you can pick it up and then we can go get it tested and see if it is actually meteorite. Or did it drop off of an airplane? But if it's going to have a coating like this, if it's a dark crust, the fusion crust, it could very well be a meteorite. We're looking a little bit more on the edge. Oh, and these shiny bits here, this is all iron. All these little shiny pieces. These are little flecks of iron, and you can see it's starting to rust around because this is not stainless steel. There we go. Shiny bits like that. That is a piece of iron. All these little shiny bits are iron. So when I take magnet, well, this is a really small sample. It's hard to get a magnet to pick up on. But if I just rotate it, you can see shininess is coming off. So all these are little flecks of iron. And you can see the little round chondrules in all of these. So I think this is one of my prettier ones on the inside. I've gotten lots of people who said they would love to have a countertop made of this. That would be rather one expensive countertop. The issue is really Oops, let's get the wrong direction. There we go. The issue with this is really getting enough material to make a single countertop, because this is just one little rock. This is a 7-gram end piece. Show you the side. Go. That's a zoomed in view of the fusion crust. There's some cracking on it, some crackling. That's what it looks like. But it's dark. It looks burnt. Got little pieces where it flaked off. This is probably just weathering. Or as it went through the atmosphere, it just popped off. As it was going through the lower atmosphere to the stratosphere, little bitty bits may have fallen off, or it may have fallen off once it impacted the ground. There's just no way of telling. But this is the little end piece. And you would never know when you cut it open, the inside, like this. So any one of these meteorites that I have, it may look like this. It probably doesn't. It probably looks completely different. So while we're looking at this one, we can also take a look at another one. So I'm going to switch the view, and this is Northwest Africa 443. This and Northwest Africa 4433. That's a little bit of a reflection right there. We'll see how this goes right here. And I'm going to see about knocking down just a tad. Let's get a little bit darker so you can see it. There we go. Northwest Africa 4433. And looking at this, it has the fusion crust on the outside, just barely there. But the inside is totally different. It's a really pretty streaked color. And if I flip it over the other side, we can actually see a little bit of iron flecks all throughout it too. This is a irregular slice of the rock. Just to see what the inside looks like. It's a very, very nice polish. Switched over to the microscope view. Oh, all right. That may not be the best of ideas, just because this is a highly, highly polished piece. So what happens if we zoom way in? Yeah, I don't think this is going to be a good one, because this piece is just super, super polished. And it's picking up the reflection off of the lights. I would have to do something totally different with this one. But we can see some chondrules and all these little iron flecks. So these shiny bits right here that we're seeing, those are little bits of iron as well. Let's see, where is it? There we go. That right there is a little piece of iron. All these little shiny bits all through here. These are all pieces of iron as well. They're just really hard to see because of the shine on this, which is really too bad, because this is a very, very lovely one. Very pretty. It's just so super shiny that it's hard to really see what's there. Playing with the lights, there we go. Be slightly better. So looking at some others, we have Northwest Africa 4404. This is another one. Again, you can see that there is a very nice polish to it. This one looks totally different as well. There is a fusion crust on it. The fusion crust is very, very dark. I put it down. The inside is this really pretty brown color. Looks different than the outside. I play with this just a tad. I'm gonna get the best lighting on this, and just because there's so much polish on it, it's really hard to see. Sorry about that. Here is Northwest Africa 7161. This other one with a lot of polish. This one has actually a lot of shininess to it. As I move it this way, all those little shiny bits, that is iron. So if I take a magnet to it, I can actually lift it up just from the iron in it. This is one way that we know that meteorites aren't Earth rocks. If we look at Earth rocks, they typically have very, very little iron in them. Meteorites have anywhere from, some have none. So point blank, some have none. But most meteorites, especially of asteroid origin, are going to have some iron in them. And that iron usually has a lot of nickel in it, a lot more nickel than Earth rocks do that contain iron. So by analyzing the amount of nickel in the iron of a meteorite, we can determine that, yeah, it's extraterrestrial. It is not an Earth rock. So for this one, there's quite a bit of shininess to it. And we can see a bunch of chondrules as well, either side. Let's see how well this one goes under the microscope. Don't know. We'll find out. It's a bit shiny. That's okay. Let's take a look at, get the focus a little better. Yeah, this one we see just a lot of chondrules to it. So a lot of these round bits. We can see one right there in the center, that brown or the that black round bit, and we have the shiny iron flecks all around there. More chondrules. If you have any questions, go ahead and put them in the chat. I'm glancing over there and watching. A lot of little bits of iron, but all these little chondrules. Some are bright, some are dark. Let's see. There is a large chondrule, and looks like it's got something around it, some type of accretion around it. So this one right here is the chondrule. This is some type of accretion around it. The black and these white bits, like a little shell. But we see more chondrules. Here's a black one right here. Oops. That one is a chondrule. And then we have another one here on the edge. Just quite a few. As we go through, we just see more and more chondrules. So that's why we call these chondrites and these rocks chondrites. So these chondrules are we can think of as tiny little time capsules from the beginning of the solar system. So most of the meteorites that we're looking at are going to be chondrites. So what chondrites are is a stony meteorite with a little bit of iron in it, and we call them stony meteorites. Then we have stuff like these. This one is a iron meteorite. It's fairly small, not that easy to see, but we'll take a look in a second. This one is from Poland. This one's called Microscopic. And this one was actually found from an impact we think, I don't remember, I think it's 9,000 years ago. But it was discovered in the early 20th century. In Poland, there is a group of, I believe it's 11 craters, and 9 of them are filled with water, little bitty ponds. So Microscopic is a iron meteorite. It's this one is cleaned up. So typically these are going to be found with a lot of rust. Iron for meteorites tends to rust fairly quickly in the atmosphere, or sorry, on Earth. There are actually there's a Chinese palisite which actually has a lot of chlorine in it. And that chlorine causes it to rust if you just look at it sideways. So it's actually rather popular for pendants, little pieces of jewelry. The issue is that if you don't have it covered in oil, if you don't have it covered in resin, something which keeps the atmosphere, specifically water vapor, away from it, it will rust. So people will go ahead and buy them thinking they're very pretty and leave them in their jewelry box and come back 6 months later and it's a pile of little peridot crystals in a surrounded by bits of rust flake. So this one, you can see, very, very easily comes off. of the case with the magnet, so it sticks quite a bit to it. And I know I actually had some magnets here, and I found them. Oh, excellent, good, good, good. Okay, I have these little stick magnets, and I like these little stick magnets because they're small, they're lightweight, but they can really show. They can really show something that has iron in it because they'll just kind of stick to it like this at an angle. They're just stuck to it. So the quick and dirty way of checking to see if something could possibly be a meteorite is just using a magnet, seeing if it sticks. So in this case, it does. So this is we've seen the stony, we've seen the iron. Now we have one of the stony irons. The stony irons are a mix. So we think the iron meteorites come from they're the remnants of the core of a asteroid that got blasted apart. This one is iron peridot crystals. A lot of polish on it, so it's really, really bright. But this one's starting to rust, so I have to clean this off soon. It's actually starting to fall apart too. I haven't really done anything with it, but I will clean it up, take some of the rust off, and do the best I can with it. But the magnet sticks to it very well because this is mostly iron. So iron meteorites come from the cores of asteroids that were large enough to be differentiated. So think of it as several hundred kilometers across, something big enough that the material during the Great Bombardment phase, the material was accreting together into a single body. It generated heat. So we have potential gravitational energy as it's impacting. It turns into kinetic energy. All that material is melted. So the iron there melted as well. And because iron is heavier than silicates, the iron traveled down and created the core. The silicates floated on top with a crust on the mantle. Well, on that interface between the mantle and the core is where we get the pallasites. Pallasites are a mix of olivine crystals from the bottom of the mantle with nickel iron, molten nickel iron at the top of the crust. So they're a lot rarer than just iron meteorites. So for this one, what we're looking at is this mix of the peridot crystals, which is all the stuff around here that's not shiny in iron. We call it olivine, but olivine and peridot are the same thing. The olivine crystals in an iron matrix we call a pallasite. So you can actually find these that they're cut in very, very thin sections so that the crystals can be backlit and you have bright enough light. The iron blocks the light, but the light passes through the crystals and it's this yellowish orange color. It's quite pretty. But these are fairly rare. So it's hard to get a good size one, and they do tend to rust just because it's iron. So I have to clean this up, and the way you clean this one up is you use isopropyl alcohol, and you very, very gently scrub away the rust, and then you coat it in either resin or in a gun oil, and that prevents it from rusting. And you have to keep ironing it. Keep oiling it to prevent it from rusting. So again, so we've looked at irons, stony irons, and stony meteorites. So that's kind of a quick sample of all three different types. And again, this one's kind of falling apart. I'm putting this one under the microscope. I'm not sure what's going to happen, but let's just find out. Might as well, right? That time. Here we go. So here, you see a whole lot of rust. All the shiny stuff, that's the iron. All the black stuff like this, that's the peridot crystal. Here we go. So we can see the peridot in there, and light is lighting it up. The bits on the edge there, that's more of it's that kind of interface. That's where the peridot and the iron are kind of mixing together into kind of a weird alloy. But the peridot is found at the lower bits of the mantle on Earth. That's brought up in certain places of the world and mined. Um, it's pretty. It's a pretty yellowish kind of orange color we got. So let's see if I can find any more. Oh, here's another pretty one. So the black part of this is again that kind of weird mix of peridot and iron. Where the peridot, the outside of it melts into the iron, and the iron changes, and the inside is that undisturbed crystal. Uh, so if you have a big enough piece and you slice it thin enough, and hope that the structure of the crystals is strong enough and the iron is strong enough, it doesn't crack like this one is. Um, you can make some really pretty pieces out of it, either jewelry, a pendant, or something big that you can then backlit. You can find these if you go on eBay. You can find them as well. Um, that's a fairly large one right there. And these crystals aren't really gem quality. Um, you can see that they're kind of chunky. And because this is already sliced, they're not going to be very big as it is. I suppose if you had one, you can always melt the iron away and get the peridot, um, and I don't know, filter them out and do something with them. Not 100% positive. I don't remember what temperature peridot melts, uh, but there we go. So the bright shiny stuff, that's all iron. The dark stuff is the mix, and the yellow stuff is the peridot crystals. And that red stuff right there, that is rust. So that is the iron rusting away that I've got to clean off. And you can see that rust is actually causing it to fall apart. If I get to the edge, you can see it right there. The rust actually caused parts of it to flake off. And this is a piece that broke. So you can see the iron right there. It's quite pretty. But this is unpolished iron. This is just cut. I guess it's cut and a quick polish on it. But it's not etched. So what does iron look like from the core of an asteroid? Well, if you think about it, when we do ironworking on Earth, let's say it's smelting, it's just blacksmithing, it's ironwork in general. Um, we make different types of irons and steels for different purposes. So you can make a steel. It's just called a steel. You can make a steel that's very ductile. It's very soft. You can bang it, bang it, bang it. It will bend like spring steel, but it won't necessarily break, or it won't break easily unless you really, really bend it a lot. We call that ductile. Then you can have iron that doesn't bend, but it's very, very, very strong. It's only strong to a point, and it snaps. We call that brittle. We have ductile metal and we have brittle metal. And what happens is if the crystals um, are small, then the metal tends to be brittle. If the crystals are large, it tends to be ductile. Uh, it's just the strength of the bonds between different crystals and how those crystals can move. It's a whole lot of factors, and I am not a blacksmith. But the inside of an asteroid, what we have is a core that cools down very, very, very slowly. When you're doing blacksmithing, what you can do is, let's say you have a piece of metal, you heat it up till it's red hot, and then you can either let it cool slowly in the air, or you can quench it. So you can take it and you can put it in water for a very, very quick quench. You can also take it and put it in oil for a different type of quench. And cooling it down to different temperatures at different speeds changes the metal. Well, on the inside of an asteroid, that metal nickel iron is being cooled down very, 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 very slowly. And when it does, you have crystals that form that are much, much larger than what you see on Earth. Uh-oh. Looks like I ran out of power on the light here. Okay. That's right. You can see these crystals pretty well right here. And these, I have this in a bag because this is quite oily. And I will eventually have to put this into some resin, covered in resin. You can see the crystals in this piece of iron. See the difference in the colors as I rotate it. Okay? All those big pieces, those are crystals. So in here, there's a crystal. Do this way. Crystals here, crystals here, crystals here, crystals here. Long crystals. I turn it. See crystals all through here, different orientations, and they have different names depending on the amount of nickel in them, on how they look like. So these are rather flat looking ones. And if I take a look at a different one, this piece look like little needles. Again, sorry it's in a bag, but this is quite oily and it's rusting and it's going to be falling apart. So you can see these are needle-like crystals. And we call these Widmanstätten patterns after the German guy who discovered them. And we get these patterns out of the metal through a very simple process of this way. There we go. We take the iron meteorite, we cut it very, very thin, and then we polish it. So you polish it until it's nice and shiny, and you take a nitric acid solution and you just wipe it on the surface and give it 20, 30 seconds, and then you wash it off, neutralize it, and this pattern comes out. And what's happening is that the nitric acid etches the surface in different ways depending on the crystal. So on the crystal type. So some bits get etched more than others. Let's see what this looks like under the microscope. Let's see if there's going to be, let's see just how visible this is going to be because I'm not really sure. Focus. There we go. So now we can see the interfaces between these crystals. So this is a fairly large crystal right there. You can see that they are actually touching, but there's space in between. And that space in between is just where those crystals touch. So if you dealt with anything else, with any other type of crystal, you would have the same thing where two crystals are, when they're forming, they butt up against each other and then they stop forming because they don't form into each other because those two structures are separate. You have atoms which are aligned in this direction, let's say, let's say like atoms aligned in this direction, then you have more, or atoms aligned this direction. Atoms aligned in this direction. And when they're coming together, they can't go through each other, and so they just kind of stop. And it creates this interface layer between the crystals. You can see this was polished. But all these different crystals are just kind of butting up against each other. So this is what you get when you have a situation where iron is able to cool down slowly, slowly, slowly over millions to tens of millions of years. You have these large crystal formations. And because the iron is cooling down very slowly over a long period of time, this is one way we can tell that a piece of metal is definitely extraterrestrial. If you cut it, if you polish it, if you then etch it, and these Widmanstätten patterns come out, we know this has to be extraterrestrial. We know this had to have come from the core of an asteroid, and that there is no way that we can replicate this on Earth. We do not have the ability to cool down a piece of metal very slowly from molten state to solid state over even tens of thousands of years. So we cannot create crystals like this in iron on Earth. If you grab the other one, let's see what it looks like. These are rusting and falling apart. That's okay. We'll get them fixed. So here it's going to be a little bit harder to see. See if we can get the other side. No, this is going to be the best bet I have. You know what? I'm going to pull this out. This is in yet another baggy. Oh, man. Yeah, I'm not terribly happy. And it's really my fault. It's just a matter of time. Finding the time to do it. There we go. This was not polished terribly well before it was etched, but the etching, and actually you can see the polished lines, the cut lines. Let's see if we can find something a little better. Not terribly. All through here. Zoom out. I hope this works. There we go. So we can see all these crystals, and they're coming in all sorts of directions. And you can see some of these look like they're overlapping. Right here, looks like this crystal is overlapping these, and it is because these crystals are three-dimensional in nature. They're not lying in a flat plane. They're from the core of a large asteroid. So these crystals are growing in every single direction, all up against each other, and some of them are across the cut plane, some are through the cut plane, and so they appear on top of each other, through each other, just in every possible direction. But you can see the pattern, this kind of triangular or hexagonal pattern. Well, it's very triangular that you see. That's the oil spot right there. So the angles at which these particular ones intersect each other, well, close to 120 degrees. And it's a really, really pretty pattern. And again, you can only find this pattern, these types of iron crystals in meteorites from the cores of large differentiated asteroids that got blasted apart. Now I've got little bits of meteoritic iron floating all around my table here. I will have to clean this up, but they are rusting away. I will have to deal with it at some point in the future. Not right this moment, but soon enough. What are we looking at? We're looking at. Oh, one more thing about the. Oh, whoops. That's the wrong button. I didn't actually intend to hit that button. I intended to hit this button. Sorry about that. If you have any questions, any comments, go ahead and put them in the chat, and I'll be looking at them. Something that is interesting, meteoritic iron is the very, very first iron that humans ever learned to use. If you look up Tutankhamun's dagger, King Tut of Egypt, his dagger was made of the blade is meteoritic iron, and the handle the hilt is gold with jewels. It's very, very pretty, but it's an iron blade. At that time, iron was incredibly expensive. It was probably far more than gold, and it's the first iron that humans learned to manipulate because we don't really have any free iron on Earth. All the iron that we have is bound with oxygen into iron oxide. So when we dig up iron out of the ground, we're actually digging up rust from the banded iron formations. And we're then taking that and smelting it and turning it into usable iron and eventually steel. The banded iron formations, they come from a time before, actually, well, the Earth's oceans used to be green. before cyanobacteria and algae uh, were spewing out a lot of oxygen. Um, the atmosphere was mostly carbon dioxide and methane and a bunch of other gases, but there's very, very little free oxygen. And at the time, iron was dissolved in the water. Iron dissolves readily in water in certain conditions, as long as there's no oxygen present. During the Great Oxygen Crisis, when you had the cyanobacteria, the blue-green algae spewing out a lot of oxygen, that was basically a poison, a waste product. That oxygen was dissolved into the oceans. When the oxygen level of the ocean rose to a certain point, within I think about 10,000 years or so, or even less, the oceans went from green, which is the color of the of dissolved iron in water, to rust red, a thick, opaque rust red, and then all that rust precipitated out onto the seafloor bottom, and eventually got covered over with sediment and compressed and folded and whatnot, and um, those deposits are now, we call them the banded iron formations, and that's where we get our iron from the iron that used to be dissolved in the oceans. Or we got it from meteorites. The very first ones were meteorites because that is free iron that we could manipulate. So there's actually Ulfred, I think that's what it is. There's a line of Viking swords that have a component of them, of the iron, as being meteoritic. We know that the Inuit in Greenland, there was a very large meteor, an iron meteor in Greenland that was used as an iron mine by the Inuit, and that's where they got their iron for their tools, for knives, for spear tips, harpoon tips, and I don't know if you noticed, but there's not really any trees in Greenland, so it's very, very difficult to heat up iron to the point where you can actually do something with it. So the Inuit use what's called cold smelting. They picked up a rock and used that rock and hit chunks of iron off that meteorite. And by the way, this thing was several tons. I want to say 8 to 10 tons, somewhere about there, of iron. And they just kept knocking off chunks of it, and then they would take those chunks and hit them with rocks, put them on a rock, hit it with another rock, and this is cold forging, and fold them and beat them and fold them and beat them, and eventually turn them into a usable tool. It's perfectly serviceable. It's not going to be nearly as strong as, excuse me, as like doing blacksmithing, and there's limits to what you can do with it. But it worked well enough for them at the time, until eventually, I believe it was an English explorer that found it and stole it and took it back to England. So, which is really too bad. But nonetheless, there we are. So humanity's first iron came from iron meteorites. All right, what else we got? You have several. So I actually started collecting these not too many years ago, just because it was interesting. Then I started getting more and more to use for outreach purposes for the Fort Worth Astronomical Society. The neat thing is, every meteorite tells a story. So each one has a history behind it and tells what happened to it from earliest until when it was on the Earth. So here, start off with this one. Here we have meteorite. This is pretty much what it looked like when it was on the ground. This was found Northwest Africa. This one does not have a name. If a meteorite is analyzed, if you find a meteorite and you want to know what it is, you'll send it off to be analyzed. And there are actually several meteorite labs around the world. There's one in Germany. There's one in, I want to say, I don't remember if it's Portland or if it's Seattle. It's in the Pacific Northwest United States. I know definitely there's one in Japan, and probably one or two others in Europe. But you can send a meteorite to be analyzed. And what they typically do is they'll cut a piece off it or slice it and see what the inside is like. They'll analyze the iron. They'll analyze it for the chondrules, see if it's from an asteroid, see if it's from a planet. It could be from the moon. It could be from Mars. See if it comes from a known asteroid, things like that. Analyze it, figure out what it is, and classify it. And once it's analyzed, once it's classified, it can get a name. So it needs a provenance. Where was it found? Um, when was it found? Was this an observed fall? Was this just a find? And the difference is a fall is you actually see, or somebody sees a meteor flying, or bolide even, a fireball going through the sky. And you see it, and it goes from, let's say, from north to south. And then you go out looking in the place where you think it fell, and you find fresh meteorites, or a fresh meteorite. Several rocks, one rock, but they look fresh. That would be a fall. If you're just walking along and you find a rock on the ground, that's a meteorite. That is a find. We have falls and we have finds. This was a find. It was just a meteorite lying on the ground. Let's look at it. It's got the patina. It's got this. It's got the fusion crust, but it's all cracked in here, isn't it? It's got this crackling on it, and it's not shiny. It's definitely not shiny anymore. It's smooth, but it's kind of roughed up. That's because this thing's been sitting on the ground for who knows how long in the Sahara, and the sand has been blowing over it and sandblasting it for who knows how long. Could be 50 years, could be 100 years. I have no idea. I'm not an expert on sand weathering rates in the Sahara or in the part of the Sahara where this was found. So all we can say is this is a weathered, what do you call it? A weathered meteorite. So that's what we got. We can tell, because I have another piece of it, is that on a different part, the fusion crust on here is unweathered. So this is actually the bottom of it. Now let's look at this. By the way, this is the same rock. Very, very similar. It's the same rock. Here's what we're going to look at. This one, it's easier if I just leave that one there. This is a rock with some history. So already we know it's been on the Earth for 50, 100 years, who knows how long, in the Sahara, sitting on the ground, weathering before anyone picked it up. When we slice it open, the inside looks completely different than the outside. It's not dark, it's very light, but it's got all these lines in it, which is it's quite strange, isn't it? It's not really typical. We don't really know just from first glance what this is, but we do know that magnets stick to it. Magnets stick to certain parts of it, actually better than other parts. So I use this as kind of a probe. So magnets sticking to here, not sticking too much to there, but as you can see, I'm moving it across and it's jumping. It really likes this part right here. As I move it across, it just wants to stay right there. I'm just pushing it lightly. It really just wants to be there. There's another portion here. This is another iron, a little bit of iron right there. At that point, we're looking under the microscope to see, but there's a bunch of shiny bits. And if I turn it this way, you can see all those little shiny bits all through there. They're iron. So we know that this is it's a stony meteorite with a little bit of iron in it. Well, then it's got these interesting cracks in it in that color. These are what are called shock cracks or shock features, shock fractures. So we know that at one point, this rock may have been on an asteroid, may have been part of an asteroid, may have been part of a bigger structure, bigger rock that got hit very, very, very hard by another rock. Hard enough that it squeezed it together. It cracked it along these lines, and that this red color, this different color all through here, this is metamorphic material. So it squeezed it, cracked it, and squeezed it so hard that it actually melted along those lines and then resolidified. We can also see on the other side these lines. So these are the continuations of the cracks clear through the broken part. So this broken part means that it probably in the atmosphere after it was a meteor and it was just tumbling, it broke apart, or at least at the last part of it of its journey, it broke apart. So you don't really have any or very little fusion crust on this broken part. You have little bits and pieces, but not very much. A little bit of darkening all through here. But these cracks here, let's say this feature right there, it's got a little lip to it. This metamorphic material is stronger than the surrounding matrix. So when it cracked, these fractures, these remnant fractures, are higher up than the matrix around them. That's kind of the history of this rock. This rock was through some type of a collision event early in its life, or at some point in its life, that caused it to structurally change before it landed on the Earth. So this rock also has a history, and by analyzing it, by looking at it, we can tell what it is. So let's see what this looks like. This is highly polished. I really like this one. This is one of my first ones. You can see all that shiny stuff. These are the flecks of iron. It is still an a stony meteorite, not an iron meteorite, iron or a stony iron. But it's got a lot. You see, the metamorphic part is very shiny. The iron bits are very shiny. The gray material, it's not really shiny. Metamorphic material, that reddish part, that takes a shine really well. So does the iron fleck, and you can see the iron flecks right here. That's a big one. That's a big one right there. It's got some more right there. Just all through here. Iron there. Oh, no, not right there. That's a bit of iron right there. All through here, that's a little bit of iron right there. But this is the nice big fleck right there. And then all that red stuff around it. If we look at one of these fractures, from above, it looks like it's cracked and broken. But when we look at it here, and in fact, I'm going to zoom in. Let's see just how close we can get this thing. There we go. All right. So we're looking at these cracks right now. Take a look at what that looks like. These cracks are filled. It is not a fracture. It is not a crack, if you think of it like a crack in the sidewalk, where there's a separation between the two sides of the material, between either side, and a void in between. This is actually filled in material. So it was squeezed hard enough to crack it. It was squeezed hard enough to melt it, and that melt filled in the inside. So this is this is actually really interesting for the history, and it tells you that it is not a piece of broken material. It's not rubble. Excuse me. When it was squeezed together and melted, it stayed an entire piece. It was still one chunk of rock. It was just fundamentally changed from this impact. And I think this is really interesting that we can actually see the fine structure in this and be able to tell that, hey, there, it's a good example right there, that it's not, it's fundamentally different than what you would see on Earth rocks. When you see cracking earth rocks, it cracks. It cracks. It breaks apart in multiple pieces. This isn't that same scenario. There's essentially you can consider it a cement on the inside, but it's metamorphic. And the rock there is fundamentally changed. It is cracked. It was broken, um, but it's still together, and those cracks are filled. So it's think of it as, you can think of it as almost self-repairing material. It was just a serious impact that created this. Okay. So Cyberplayer 5 asking those microbes from the pre-oxygen era of Earth, the same microbes we see today near the deep sea volcanic vents. Those, I believe, they're kind of remnants of what early life was on Earth, but the stuff that actually created the oxygen crisis, that was cyanobacteria and early blue-green algae. Um, its waste product was oxygen, and the seas filled with waste. That's what it was. So oxygen-breathing organisms then evolved because it was either evolve or die. Oxygen is a poison to some of these uh, we call them some of these organisms that are that don't use oxygen for respiration, but they use something else like is it hydrogen sulfide or something else for electron transport. Um, it's been a while since I took biology, so I don't remember all the details exactly, but yeah, what we're talking about is the flourishing of cyanobacteria that caused the first oxygen crisis. All right, back to the meteorites. So, what are we looking at? We're looking at this one again. This is Northwest Africa, unclassified. So, if we have like the previous ones that we were looking at, Northwest Africa's, if they don't, we just call them Northwest Africa unclassifieds. If they haven't been analyzed, they haven't been cut open and sent off to a lab, found to be interesting and given a name, we just call them unclassifieds. So we know where they come from, but think of it kind of like uh, actually, I cannot think of a suitable analogy on Earth with anything. Um, so maybe diamonds. I guess you could say, or gemstones in general. So if you have a gemstone, let's say you just find a diamond. You got to, oh, I believe there's that diamond mine in Arkansas. If you go out there and you find a diamond, it is, we call them diamond in the rough. It is a rough crystal. It can be big, it can be small, but you may not know what the inside looks like, especially if you're not an expert. So, in the same case with meteorites, you can have a rough, uncut meteorite. Um, it's not it's not terribly pretty. It's not beautiful, and you don't know what the inside is going to look like until you cut it open. And I happen to like these bigger ones because I can actually take these like and show them off, and I can say, now let's put this back on. So what I like to do is take these meteorites and actually put them in people's hands and say, um, hold this, see what this feels like, see how heavy this is in your hand, compare it to earth rocks. So if I compare it to earth rock over here, what does that look like? What does that feel like? And actually, when I go, or well, I should say, in the before times, what I would do is if we were going out to a an outreach event, I would have a number of other rocks. I take them out. I would say, for the kids specifically, which ones are earth rocks, which ones are meteorites. And I would show these off, and I would get usually kids, but adults as well. And I'd put out the magnets. I'd have the magnets, and I would say, well, which ones are earth rocks, which ones are meteorites. So magnet sticks to that one. Magnet really sticks to that one. And there. And these are just little stick magnets. That's all that they are. Little fridge magnets. You can see right there. Grabbed it. This one's sticking up out of it. Well, these, nothing is sticking to these at all. It just rolled right off. So that tells me there's little to no iron in any of those. Excuse me. Not all meteorites have iron, and magnets won't stick to every single one, but this is a pretty good preliminary test. And then there's a surface, so they can see the meteorite's a lot darker than the Earth rocks. So these are all fairly smooth. This one's weird. It's totally different than the others. And it's heavy for an Earth rock, but it's a lot lighter than the meteorites. This is actually a piece of lanite. This is a granite with bluish purple quartz crystals in it, and you can only find this down in near Llano, Texas. And there is an outcropping. I want to say it's Highway 6. It's whatever the highway is coming north out of Llano, Texas. Couple miles, 20-something miles north of Llano-ish, somewhere about there. And near Baby Head Cemetery, if you're taking that road, there is an outcropping there. It is a dike. It is a volcanic dike. The dike is composed of lanite, and that is the only public location in Texas where you can find lanite. And it is a very, very hard rock. You need a sledgehammer and a big chisel to knock off pieces of it if you want any for yourself. But it is still less dense than meteorites are, and essentially less hard. Very pretty when polished up, though. This is a nice smooth rock, but this is limestone, which we find all over Texas. Excuse me. Again, not a meteorite. This is, I believe, a piece of gneiss. It is a metamorphic granite. This one is from Colorado. I remember picking it up when I was a kid out of a riverbed. It is smooth, it is pretty, but it's not a meteorite. This is smooth and weird and shiny, but this is some type of a siltstone. This came out of my garden. It is still definitely not a meteorite. I had one more somewhere. Where did it go? Oh, here we go. Let's get this guy in. Oh, that's just weird looking. It's orange. It's smooth. It's kind of knobbly. It's really smooth. It's actually a lot smoother than this. But it's got this calcite vein coming through it. It's probably another siltstone of some type. A big old calcite vein all through it. This is another earth rock. It is not a meteorite. So, again, well, magnets, nope, doesn't stick to it, just comes right off. So this is something that we can do on outreach events, is actually have people hold meteorites, touch them in their hands, take a magnet and poke around and see. There you go. So you can see it's sticking. It's definitely sticking to these, and these, not at all. So this is a good test for kids and adults, just to be able to see right away, hey, these are the physical differences between meteorites and earth rocks. It lets people experience it directly firsthand and not just through a book. Books are fantastic. Books are great. You can learn a lot from books, but sometimes that just having that in your hand, just being able to feel it, it drives the lesson home in ways that just reading it might not necessarily do. And we are now hopefully soon coming out of quarantine status. We have been doing previously this month we did do a public star party, but I don't think we're at the point yet that I'm going to be taking the meteorites out to have people hold on to them. We still want to do social distancing and separation from people, um, just in case. And I don't know everyone's vaccination status. So, and I have a little one at home who can't be vaccinated yet. So I'm not willing to bring something home for him, even though he did bring something home for me. Speaking of which, um, so there we go. So this is the hands-on portion of what I would typically show. Now, as a quick aside, buying meteorites, because I know someone's probably interested. People are going to ask, where do you buy meteorites? Well, you can buy them in several places. I would say always buy them through a reputable dealer. There's the International Meteorite Collectors Association, uh, and people and reputable dealers have memberships. I don't because I'm not a dealer. I don't sell my own. If I started to sell, I would definitely get a membership. I find it really interesting, but this is really for myself and for outreach purposes, not for making any money. Um, but find a dealer, a reputable one. You can find them online. There are a number of them. Um, I've gotten mine from various sources. I have a dealer in Canada. I have worked with uh, two guys out of Poland, two meteorite hunters. So they actually source the meteorites themselves. They actually go out. They look for them in Morocco, or at least they did in the before times. Um, they find them themselves, get them analyzed, cut them, polish them, um, and it's finding people that you trust and building a relationship with them, and knowing that their material is good. I do not recommend buying stuff on eBay unless you know exactly who the dealer is. And there are several uh, reputable ones off of eBay, but there are also people who are not reputable. And I learned my lesson. It wasn't a terribly expensive lesson, but I found an auction on eBay, and I thought it was rather interesting. And I thought, you know what? Not terribly expensive. It's only $80. You know what? I'll try. Oops, crashed on my table a bit. So I got this thing. It kind of looks like a meteorite, doesn't it? It's smooth on the outside. It's got that patina on it. It's got that kind of brownish black look, but it's got all this lighter colored stuff on this. I know it's not quite in focus. That's fine. Uh, so looking at this side, it looks different. It's actually flat on this side, and it's got these holes in it. There's a hole right there. Is that is that a regoglyph? No. So iron meteorites, they typically have these things. I believe they're called regoglyphs. It's a thumbprint where it looks like someone just stuck their thumb in and kind of squished out a bit of it. And what these are places as it's passing through the atmosphere, um, the air is creating a whorl, and it's eating out a bit of the material. You see this exact same phenomenon in rivers, where you have, let's say, a large flat rock, and there's a little bit of depression in that rock, and then maybe you have some pebbles on the inside or some sand on the inside, and when water washes over it, it creates a little whorl in there, moves those rocks around, moves that sand around, and etches out a little depression, a little hole. And the bigger it is, the faster it develops, because that hole uh, keeps the rocks inside, keeps the sand inside, and that just scours the outside as the water goes through and circles around and around. Same thing on the rock. As it's going through the atmosphere, it's just very, very fast. You have superheated air that gets into a little a little depression and starts whirling and like very quickly eats a little hole through it or into it, I should say. Um, don't really see any of that here. But if I take the magnet, oh yeah, magnet really sticks to it. Will not fall off. It sticks up quite well. Yep. So, well, it's definitely iron. It's very, very heavy. So this is definitely a chunk of iron. But could this be an iron meteorite? I thought it was. It was advertised as being a chondrite, which it's most definitely not. So a quick nickel test, and you can pick up a nickel test off of Amazon for $5 or $10. They're meant for testing jewelry. Some people are allergic to nickel. What you do is you just kind of scratch off into the outside. Sometimes you don't even need to do that, and you put the liquid on it, and if it turns green, you soak it up into little like almost like a litmus paper bit. If it turns green, that indicates the presence of nickel. The darker the green, the more nickel. Almost all iron meteorites are going to have, pretty much every iron meteorite is going to have some nickel to it, usually 5% up to like 15 or 20%. Earth steels are typically, I think it's like 2% at the very, very most, and most of them have very little to no nickel in them. So this thing doesn't have any nickel in it, at least no detectable nickel. So this is definitely an earth rock, and the report was this was found in a river, and they thought it was a meteorite. They were selling it off. So as soon as I got it, within moments of being in my hand, I knew that it was a meteorite. But test it out anyway, and yeah, it's what it is. It is Chinese industrial waste. It is a piece of iron that fell off the lip of the smelter crucible and hit the ground. Um, then folded over on this side. This is the flat side where it sat on the concrete. So it kind of down like this, and then flopped over like that, and then solidified. And when it did, eventually someone cleaned it up off the ground and tossed it into the waste bin. And the waste bin was probably eventually tipped into the river, and the river carried it a little bit downstream during flooding, and polished it up a little bit, banged it around on other rocks, and that's why it's got this appearance. But this is most definitely Chinese industrial waste. So don't worry, I didn't lose my money. I actually wrote back saying this is definitely not a meteorite. I want my money back. And they replied, if I give you half back, will you be happy? No, because it's a meteorite and I don't want to pay $40 for a chunk of waste iron. And I think a week or two went by, and then they just refunded my money without anything else, uh, any other comment or any other communication. And I'm not going to send back 1.7 kilos of waste back to China. It's a waste of fuel. It's a waste of time. It's a waste of postage. There's just no point. So this is now my object lesson on why not to buy meteorites from unknown dealers on the internet, especially dealers who don't know what they're doing, saying, I think this is a chondrite, I think this is a meteorite. And some of the prices that I've seen online are just completely ridiculous. That one, I know that's not what they have. And I'm not buying a chunk of Mars rock for $150,000 without knowing the provenance of exactly what it is and without being analyzing it in my hands before any money changes hands. But that's what the people do. They're going for someone who doesn't know, and they're hoping for the best. So it's shot in the dark, but they're trying. So I don't blame the guy too much. But this is definitely a piece of Chinese waste steel or waste iron, not a meteorite. But the cool thing is I can now take this out, and I did take this out to outreach events, and I could show it off, and I could say, is this a meteorite? And people took the magnet to it, and oh yeah, this is a meteorite. Yes, I think this is a meteorite. It's a big, heavy rock. It seems to be heavier than all the other stuff. It's really heavy. Magnet sticks to it. It must be a meteorite. And it's not. This is a meteor wrong. Meteorite, meteor wrong. It is not a real meteorite. It is not. It's not even a rock. It's just waste. And in fact, most of the meteor wrongs that people identify as they think they're meteorites, they're actually they're just earth rocks. Some of them are was it hematite or other conglomerations. They're made of iron, so the magnet does stick to it, but it's still not a it's not a meteorite. So I think there's actually a website from a geology professor, and I can't remember what it is off the top of my head, but he has a whole page, and he is not a meteorite expert. At least he didn't become. He had to become a meteorite expert, I should say. And his whole page is basically these are the rocks that people sent me, or sent me pictures of, and asked, "Hey, is this a meteorite?" 99.9% of them are earth rocks or industrial waste. He said it's rare that he gets an actual meteorite. So don't trust in stories. Don't trust uh, in what's it? Great Uncle Ted seeing a rock falling out of the sky and landing on the farm, and him going out there and having to put out the fire and bringing home this big old rock, because that didn't happen. And I've actually heard several stories. I had someone at a star party who actually told me that they were out on family land when he was young, and they saw bright meteorite come overhead, and what he said is it was just over their heads, and they could feel the heat on their faces, and it went down, and they heard it land in the forest on the edge of their property. And their dad wouldn't let them go looking for it in the middle of the night. And when they went the next day, they just couldn't find it. Well, I had to explain that, the meteor that you see is anywhere from 120 to 80 kilometers overhead. It's not just over your face, and you're not going to feel the heat unless something big like Chelyabinsk. It's just too far away. And that quick little meteorite meteor that you're thinking of, where it just zooms across the sky really fast, and then it burns out in a second or so. Those things are really, they're tiny. They're about that big, about a centimeter across, the size of a pebble or a marble. They're not very big, but they burn so bright that you can easily see it from 100 kilometers down, from if they're directly overhead. So instead, I had to kind of break that story to him. I know it's a fun story, but it's just not true. So I'd rather be right than just have a nice story. And I've actually had nice stories with my meteorites that turned out not to be true, and I'm happy I found out that they weren't true, because I would rather know more. I'd rather be right than be happy. How's that? Let's get this guy out of the way. Uh, what else we got? We have a lot to go through. So let's talk about some specific ones. So I have something interesting. Okay, let's see how well this works. I have no idea how well this is going to work. We'll find out. It's too shiny. All right, let's take it out of this. I got a nice case just to keep it safe, and this is going to work out well for this particular one. This is a slice of a rock. This one is called Northwest Africa 10331. And this one is very interesting. There are only 4 pieces of this one rock in the world. This rock happens to be primordial. What that means is this rock really hasn't changed very much at all since the beginning of the solar system. On the other side, I think this side's a little bit prettier. So there are 4 pieces of this rock. I have one. My dealer, I think he has one, or he's actually sold it in the last several months. The collector friend of his has another piece, and then the last piece was with the finder in Poland. And when I talked to him a year and a half ago, he had actually given that piece to a grad student who was working on a thesis on early solar system origins in using this rock for part of the research. So this is early solar system material. This is relatively unchanged. So this wasn't, excuse me, this apparently wasn't part of a larger asteroid. Definitely wasn't on a planet. Didn't have any impact like the previous one that we saw, where we have fracturing in it. Instead, it is a fairly pristine rock. This is good for us because this lets us look at it and see, okay, what was the early solar system like? What type of materials were there? And we can look at things like the chondrules. So we think the chondrules are remnants of the early solar system because the ratios of elements inside those chondrules match what we see in the atmosphere of the sun. That's why we think that these are from our solar system and not extrasolar. They don't come from a different solar system. They come from the initial cloud that formed the sun and the planets and the asteroids before stuff got differentiated, before stuff melted, before stuff metamorphosed into other forms. This is early solar system material. So it's very, very important for research purposes that we can have a window. So this rock also tells a story, and it tells a story of what the solar system used to be like. So let's look at this thing under the microscope. All those shiny bits. Always in the wrong direction. Always focusing in the wrong direction. Doesn't matter what I do, always in the wrong direction. Here we go. All these shiny bits. This is all iron. This is all bits of iron. There's all this shiny stuff here. This is all iron. And it's really interesting at the amount of iron in this. But this is still a chondrite. It is called, oops, there we go. This is an H6 classification, which I don't remember what it is off the top of my head. Just going through here, it's just so much iron. It's just a lot of iron. I'm trying to find a place. I'm trying to find some chondrules. Oh, there we go. There's a chondrule. So if it has chondrules, it's a chondrite. Where is it? Where is that chondrite? Up. Go back. There we go. That's a chondrite right there. That round little bit. So this is what we're looking at when we want to look at early solar system material. This is a chunk of iron. There's just a lot of iron in this one, but it is still not a oh, here we go. Black one right in the middle. That's not iron. This is a chondrule. Right there. That's a chondrule. This is a crack through it. Not sure. That crack actually doesn't penetrate to the outside. It's like an interior crack, so we don't really know the origins of it. But there we go. We got another chondrule right there. We have some other material around it. That's a rather pretty chondrule. As we come out to the edge, this one doesn't really have a fusion crust that's left. This is a weathered edge, at least on this side. I don't know what the other pieces look like, but I don't have any fusion crust on here. It's just the edge. But this is just a lot of iron. All that shiny stuff. This is all iron. And yeah, as we go through it, you can see more little bitty chondrules through here. There's one. Look at that one right in the middle. The black one. Actually, there are two right there. And we see see, up that one. And then over here, there's another one right there. Right there, that black one. Just all through it, it's just little bitty chondrules and a lot of nickel iron. If we go down here, there's just a lot of iron all throughout this. It's like these big pieces here. Okay, relatively big pieces. And more on this side. And I just think it's interesting to look at it under the microscope and see some of the structure that you can't really see that easily with naked eye. I'm going to flip it over. What do we got on this side? Some type of a inclusion. Black thing there. Oh, this is iron. This thing, yeah, this is more iron here, and it's got this white thing around it. And yeah, more little bits all through here. I don't see any obvious. Oh, there's a chondrule right there. There's a big chondrule right there. That's what we're dealing with right there. So again, early solar system material. It's stuff like this which really let us figure out that we did come from a original cloud of material, that all the planets, all the asteroids, and the sun came from the same source. That it wasn't that we don't have, excuse me, that we don't have different origins for the planets and the asteroids and the sun. That it was all it all comes from the same source, from the same dust cloud, from the same material. It differentiated later only because of stuff like metamorphosis of rocks, or fusion in case of the sun. But just looking at the chondrules, looking at the materials and the ratios of the elements, and comparing that to the sun's atmosphere, that's our indication that we all come from the same source. This is a really interesting rock, and my policy with this rock is if anyone wanted to, if anyone was interested in borrowing this for research purposes, I would be happy to give it to them on loan so that they can use it. And just add me as a byline to the scientific paper. That's pretty much all I would request. So I probably need a better case for this one. It's not the greatest of setups right now. Oh, okay. Questions, comments, concerns. Now we're going to go off into something which I find to be really interesting, and this is the asteroid Vesta, because today is Asteroid Day. So let's talk about the asteroid Vesta. Vesta is it's called 4 Vesta. It is the fourth the fourth asteroid that was ever discovered. And we sent a probe there in 2000 to 2009 or so, called Dawn, to Vesta. And its job was to orbit and image and do spectroscopic analysis of the surface. What does that mean? That means that they had a little spectroscope on there, and what its job was to look at the surface, measure off the reflected light from the sun, and analyze that light in different wavelengths as to how much light was absorbed by the surface. That absorption curve. So if you look at different frequencies of light, let's say we're just looking at infrared. So you look at infrared frequencies. So looking at something like, let's say you're looking from 250 nanometers to 380 nanometers, roughly. Whatever your range is. So you're looking for deep infrared through red into yellow or so. You're looking at a range. Using filters, you can analyze different frequencies and see what the rate of what the percentage of reflected light actually actually is. So basically, what you do is you shine one on the sun, so you know um, how much perfect reflectance is. Okay, because it's just plain sunlight, and then you train it on the surface of whatever you're analyzing. You can even use that spectroscopy on analyzing just Earth rocks, or specifically meteorites. So you shine a light on it, you measure off how much of that light at a particular frequency is actually reflected. So it can be anywhere from 100%, or it can be down to the 90s or 80s or even less. So that will give you a curve. Once you have that curve, you can compare to different materials, and you can say, okay, well, it has some of this, let's say pyroxene, because pyroxene has this particular characteristic when light is reflecting off of it in the, let's say, near infrared. This is what the light curve looks like. If you see the same signature, that means that there's probably pyroxene there on that asteroid. Well, if you do it enough on an asteroid, you can map the entire surface. You get a reflectance map of the surface, so now you know what minerals are on the surface of the asteroid. And what we figured out is, excuse me, there were apparently two major impacts on the surface of Vesta, large enough to have knocked off huge chunks of it, enough to create the group of asteroids we call the V asteroids. V for Vesta. That rocks a kilometer across, hundreds of meters across, even bigger. These are asteroids in their own right now, just because they're bigger than 1 meter across in diameter. But these are chunks of the larger asteroid Vesta. Well, from those impacts, eventually, bits and pieces landed on the Earth. And when they did, we suspected that they were from the asteroid Vesta, but we didn't know for sure until we did analysis on them. And what did we do? We cut them open, we polished them up, saw what they looked like. This is a chunk of material that is called howardite. Howardite is named after the meteorite that first was discovered with this material in Australia, near the town of Howard. And howardite is what we call this. We were suspicious this was from Vesta for a while until we confirmed it. Howardite is crustal material from Vesta. This is rock from the crust. They got blasted off, went round and around and around for 25 to 35 million years until it eventually landed, this particular one, in Northwest Africa. This particular rock is NWA 8362. And it is definitely a howardite. So if we look at it, where's my magnet? There's my magnet. A little piece of iron. Okay, there's another piece of iron. You can see from the rust. Tiny piece there, maybe. A little bit there. For the most part, there's nothing. This is the big piece right there. That's it. Everything else, there's nothing in there. There's no iron just all throughout it. So let's take a look at it under the microscope. So you can see little bitty bits of iron. I'm going to... there we go. That's a sharper focus. How's that? Excuse me. Wasn't going to be talking for this long, but nonetheless. All right. So we're looking at little tiny bits of iron, but I see no chondrules. I don't see any nice, round, globular pieces of material. What I see is fragments, stuff that's broken up. If we zoom in, let's go closer. I like this little microscope. It's quite nice. This is like $20 on Amazon. That's broken up material. That is not. Um, these aren't class. Well, sorry, these are clasts. It's broken up material. It's breccia essentially, which is typical of crustal material. Little bits of iron in it, but there's nothing round. There's nothing globular. There's nothing like little bitty balls of anything. This is all broken up. We can see sharp edges. So if I'm looking at the big gray chunk up above, so I'm looking at this. There we go. That bit. That's square. All these little bits here, these are broken up. That's broken up. This is broken up. This has sharp corners on it as well, sharp edges. None of this stuff here is round. Let's look at some of these bigger clasts like that. And the white one just below it as well. So, it's big pieces. This is a big piece. This has a very, very sharp corner right there. There's nothing in here that I can see that's round. So this isn't a chondrite. We would call this an achondrite. Even this thing, that's round-ish, that's not a chondrite. That's just bits and pieces of material. This is all broken up. What this is material from the surface of Vesta that had been impacted by other stuff over millions of years, broken up into pieces, and eventually, like this was further down into the crust, and eventually it just compressed and compressed and compressed into a solid rock. And when it got blasted off, it remained a solid rock. But this is all, you can think of this as it's just a conglomerate with that white the white cement around it holding it together. But this is definitely not a chondrite. This is not raw material. This is processed material. All these little bits and pieces here, these come from bigger rocks. It's other material, but it's not pristine. It's all broken up, smushed together, and then cemented over time. Little bits of iron. That green thing. Oh, that's interesting. I wonder what that is. That little green crystal. Could that be? That could be a piece of olivine. Um, it is entirely possible that could be olivine. There. This is that thing right there. I am not a crystal expert, but that looks to be entirely possible. It looks to be different than everything else. And hey, look, we have right around it, it's more flecks of that same material. So it could be one crystal that got broken up, and just this eventually little bits and pieces around there just got cemented together like this. So you can see rough edges absolutely everywhere. And a little chunk of iron right there. Fine pieces that are broken up, larger pieces that are broken up. There's nothing in here that looks like a chondrule. Everything's broken. There's a little rusty piece of iron right there. It rusted only because it's the Earth's atmosphere. So all this stuff really needs to be kept out of humid air. You can see right there, it's just going to start rusting away. None of these are chondrules. These are all broken up pieces that sat on the surface of near the surface of the asteroid. See, little bitty pieces. Even the little bitty pieces, they aren't weathered. And this is another way that we can tell that this is extraterrestrial. This is an Earth rock. If we look at Earth rocks, if we look at stuff like look at sandstones. So sandstones are cemented together sand. Siltstone is the same way, but sandstone, we're talking about larger grains. If we look at the grains of sand, the sand itself is weathered. So it's not sharp edges on all of them. Most of them are going to be fairly smoothed over. Why? Because the sand comes from rivers. It's carried downstream from mountains, through the riverbed, tumbling, tumbling, tumbling over other sand grains, over rocks. It knocks the edges off. So what you get is these more rounded off grains of sand by the time it eventually gets to the ocean and when it gets turned into sandstone. Sandstone also comes from desert deposits. Specifically, I'm thinking of Navajo Formation in the western United States, the Coconino Sandstone in the Grand Canyon. The Coconino is from sand dunes. So it's in the Coconino, you can actually uh, you can look at it. You can see the layers. The layers were basically surfaces of dunes um, on the leeward side facing away from the wind, where the wind pushed over the top and deposited on the backside and left. You can see these darker bands all through it. Well, if you break it along those lines, you can see stuff like fossilized raindrop craters. The raindrops hit it and eventually got covered over with sand. You can see track marks of insects and little lizards as they passed over. I believe little lizards. I know definitely there are insect tracks there. But that sand, as the wind is pushing it and moving it and moving it, it also gets weathered. So the edges are smooth. They get polished off. We don't see any of that polishing here. This is not weathered rock. This is just crushed. It's crushed, it's fractured, it's broken up through impacts. But you don't see anything like weathering on Earth. You don't see a continuous process of smoothing out edges. All you see are these sharp, broken bits. And again, this is one way we can tell that this is extraterrestrial rock and unlikely to be Earth rock, is the weathering patterns. There's also iron in here. Iron in here is pretty much the dead giveaway. When you see little flecks of iron, of free iron in a rock like this, that's going to be a meteorite. We do not have free iron on the Earth. We just don't. We have oxygen, and oxygen has been around for what 2 billion years, to the point where oxygen's gotten everywhere in the crust, and we just do not have any free iron. So the free iron and the shape of all these little bits and pieces, this is our giveaway that this is an extraterrestrial rock. So this is the Howardite. Looking at the Howardite, let's see. Howardite back in. Some neat little cases too. So we can look at the Howardite. And I'm going to actually, let's see. Excuse me. Need to find where the others are. Oh, here we go. So I have these nice little cases where, excuse me, nice little cases where I can keep all the little samples there. A nice little place where I can easily access them. Because now I want to get to some of the others that I've got here. And we're going to talk about the others from the asteroid Vesta. So what are we dealing with? We have the head group. And the head group is the Howardites, the Eucrites, and the Diogenites. So Howardites. Howardites are going to be Howardites are all crustal material. So whenever we say Howardite, we're talking about something coming from the surface of the asteroid. When we're talking about Eucrites, what we're talking about is something that comes from the volcanic formations on Vesta. Think of them as the necks of extinct volcanoes. When we're talking about diogenites. Diogenites are yet something else. Diogenites come in deep, and well, diogenites are the mantle material. So these impacts were big enough that it blasted through the crust and into the mantle. And we actually have shallow mantle material, which is regular diogenites. Then we have olivine-rich diogenites, which come from the deeper mantle. Remember, olivine is that peridot crystal that we see in the halloysite meteorites. So the deeper down in the mantle you go, the more olivine-rich the material is, until you get down to where the core starts, and olivine is like the only thing that can exist down there. Everything else melts and floats up to the top. So, what do we got? Look at another howardite. So this one, Northwest Africa, 1111447. So this one was found in 2017, again, Northwest Africa. And you can actually see, if I put these two together, they're fairly similar. Oops. Oh, let's fix that. Hold on. There we go. Northwest Africa, 11447. And it's very, very similar to the other howardite. It's very similar color, very similar look to it, very similar kind of clasts, and let's see what that looks like under the microscope. Oh. Focus. Always in the wrong direction. I don't care how I do it. It's always in the wrong direction. So this is a slice of the larger piece. We're just going to go through, and again, we can see the same. We can see a little bit, some kind of a green crystal there. I want to say it's olivine, but I'm not 100% positive. Little bits and pieces, just all scattered through here. But again, we don't see any chondrites. All we're doing is seeing a whole lot of these sharp, little, broken up pieces. And that's all we got. Sharp, little, broken up pieces. So this is howardite. This is, again, crustal material. Excuse me. Crustal material coming from the asteroid Vesta. Okay. So this one is, flip that around, Northwest Africa, 11447 howardite. This one was found in 2017. So we got two samples of howardite that we saw. Let's look at eucrite. I'm just going to put the rest of these under the microscope because it's really going to be easier to see it there anyway. This is a sample of eucrite. Again, focus. Not exactly right. Sharp, sharp, sharp. There we go. Okay. I like to say that this one looks like burnt brown and white sugar. And that brown stuff on top, the stuff that looks like obsidian almost, or burnt caramel, that is the fusion crust. So this little piece, this is Tierhert. This was Tirhert. Tierhert was found outside of Morocco. Sorry, it was found in Morocco outside the town of Tierhert. And when this thing fell, I think like 2 or 3 years before, there was actually a Martian meteorite that fell nearby. Tinduf, I believe is what that one was called. And people were really excited because they thought, well, maybe it was another Mars rock. Because the people who found bits and pieces of that one were able to sell them for a very high price because, Mars rocks were rather expensive compared to the ordinary chondrites. So when this one came down, there was a meteorite hunter, and I don't remember his name off the top of my head, but he's a pretty famous one. He was out there within, I want to say 2 or 3 days after the reports of the fireball came in. So he was out there, and by the time he got out there, there was nothing left on the ground. So he actually purchased all of his pieces from villagers who had gone out over the past 2 or 3 days, and they had picked up everything they could find. So he came back to the village, and he purchased them for a very good price. He suspected that these were eucrites, and paid accordingly. And once everything was analyzed, then this is what it came out to be. So what we're looking at right now is the white stuff and brown stuff is pyroxene and plagioclase. And these are little crystals. I swear, it looks like little brown and white sugar. And then you can see on top, this for scale, that is just a super, super thin, almost painted on layer. And you can see it doesn't extend deep into any of these crystals. It's like it's laid directly upon the crystal, like it's painted on, not like it's burned in. So we can't replicate this on Earth. Why can't we replicate it? Well, we can take a blowtorch to this, and we can heat it up really, really good and melt the material on the outside, but the temperature is still going to be less than that of what a meteorite gets when it passes through the atmosphere. So let's say you take a blowtorch to it. Well, you're heating up the outside. You're not ablating it, or you're not ablating it very much. You're heating it up, but the heat is also going inside the rock. And right here we can see the heat didn't go inside the rock. The heat didn't affect the crystals on the inside. All it did is just that quick melt on the outside. The rest was all ablated away. So that thin layer is all that's left. Again, heat doesn't go to the inside. I'm going to turn this thing around a bit. You can see it. See some more of that fusion crust. And this is kind of an interesting fusion crust. One, it's very, very fresh, so it's not weathered at all. This basically spent like, 2 or 3 days outside before it was picked up, at the very most. So there's virtually zero weathering on here. And because of the pyroxene and plagioclase composition, it's almost like obsidian. It's not like it's not like the fusion crust patina that we saw, the chondrites. It looks completely different. So let's flip it around a different way. Here's the bottom side of it. And so this is a little piece that I got from my dealer in Canada. And I got it specifically, or he gave it to me specifically for outreach purposes. So these are meteorites that I actually take out and I show. This isn't something, well, all right, let me take that back. For the last year and a half, yeah, it's been inside the house, hasn't gone anywhere. But prior to that, I would take this out to star parties. I would take this out to museum events that we were invited to. I'd take it out to just pretty much any outreach event that we were doing, just to be able to show people. And what's neat is that this microscope lets me show these kinds of things in public, hooked up to the laptop, and people can see it zoomed in on a screen much better than they can even with a like a magnifying glass. I have a magnifying glass with this, but honestly, through the microscope, you get a much better view anyway. So this is a eucrite. This comes from a volcano that was, or the remnants of a volcano on Vesta that were blasted off, broken up by an asteroid impact. Something big hit it, knocked off huge chunks of it, including this eucrite. So this piece eventually landed in Morocco in 2017, and I think it was 2017, somewhere about there. I don't remember off the top of my head, but we can always look it up. So Tierhert, Tirhert. This is the only meteorite called Tierhert. Yeah, this is a really pretty one. So this is one example of a eucrite. Well, not all eucrites look the same. Let's see what a different eucrite looks like. Here is Northwest Africa, 113. 0.034. Well, this is also eucrite. Doesn't look like the howardite, though. It looks completely different. This has a totally different structure to it. This one is more basaltic than that one. That one was crystalline, pyroxene and plagioclase. This one looks more like to me, it looks like a basalt. And again, you have little bits of inclusions. So it's these little black pieces through here and little dark gray pieces through there, where they're bits of other rock that broke off and were included in the molten rock that formed this basalt. But again, it looks totally different than that eucrite. But because they're volcanic, because they come from the same source, it is still a eucrite. We have Northwest Africa, 10364. It's eucrite. This was found in 2015. I like to label everything because there's no way that I can remember, oh yeah, this one is definitely Northwest Africa 10364. Oh, well, I mean, it is unique. The structure of it is unique to this meteorite. So, yeah, if I memorized everything, I could remember, yes, there's this one. But honestly, there are so many Northwest Africas that there's not really much point memorizing it. Label everything. If you label it, you're not going to forget it. So we have a eucrite, which is basaltic. Looks totally different than that one. Let's take a different one. We have another eucrite. Okay, this one is Northwest Africa, 11020. This is totally different as well. Completely different. This is like a darker basalt. Again, we have some inclusions. It's like a dark basalt material. Again, Northwest Africa, 11020. Another eucrite found in 2016. And it's neat. And there's not a whole lot to see. I guess if we were looking at it with I guess if we had like with a spectroscope or something else, it might show something else of interest. I just flipped it over, see what's on the other side. But we see a bunch of inclusions. There's this black matrix around it. That's a basaltic material, so it's rather dense. But there's no iron in it. Let's take the magnet. Highly doubt there's any iron in it. How's that? Nope, absolutely nothing. It's not moving, doesn't stick to anything. There's no iron in this one. So, but this is still eucrite. This is still volcanic material. Vesta. Okay, what else we got? Here's another eucrite. This is no, that's the one we just looked at. Yep, here we go. This is Northwest Africa, 12460. Yet again, we have a darker basaltic material with some inclusions in it. Yeah, we should call them inclusions. Got a crack in there. All those lines, those are actually cutting lines. So when it was when the whole rock was cut into small pieces, it left these little striations. But again, it's a basaltic material, and Northwest Africa, 12460, and this one is eucrite and found in 2018. So interesting, nonetheless. It's just additional material. It's just another sample of volcanic material from Vesta. Ooh. I think I have one more eucrite. I'm pretty sure that's what this one is. And it's yet another. This one's kind of interesting. This one's got vesicles in it. See those holes? Yep. This is actually something that's very, very interesting, and this is rare. Okay, I will say right now, this is Northwest Africa 8266, Eucrite from 2014. Okay, so vesicles in meteorites, little holes. Uh, these are very, very rare. And one of the things that we can say is if you have a big rock with big holes in it, it is probably not a meteorite. Actually, we would say this is definitely not a meteorite, except for the fact that we have found a couple of meteorites, and apparently including this one. We found a couple of meteorites that have vesicles, that have holes in them, but they're very, very, very rare. I believe there is one from there's one lunar that has vesicles. There's just one lunar meteorite that has vesicles in it. I think there's one or two from Oman. JAH. I forget what JAH stands for. I gotta go look it up. So there is a. Man, I'm gonna look at it. It's my paperwork here. So there is JAH, and I think there's one of those that has vesicles in it, and they're fairly large. This one looks to be another one. Um, and at first glance, what you typically say is, yeah, if it's got vesicles in it, yeah, it's not a meteorite. It's industrial waste. It's 999,999 times out of a million. It's going to be slag. It's going to be industrial waste, the kind of stuff that you find. JAH chondrite. Yeah, this is not it. So, sorry, JH. You know what? Man, now I've got to go look it up. Good thing I've got something right here. So if I look it up, I do. Let's see, Google meteorite vesicles. I don't know, just vesicles, meteorite. Because I know that there is. Yeah, cold from a liquid. Yep, vesicles and amygdals. So we have amygdal is what we would call it. It is a gas cavity or vesicle in an igneous rock which is filled with secondary minerals such as zeolites, calcites, quartz. But in this case, we actually have a void. So there is, there's a sample from Apollo 17 that has vesicles. It's a basalt that was found on the moon. And then we have some eucrites. A few eucrites and diogenites are moderately vesicular. Not very many. So there are a couple of eucrites and some diogenites. So that's rather interesting. There are very, very few that have these little vesicles. So that's actually cool. This is it. Wow, I didn't know how rare this one was. But there we go. So this is a eucrite that has some little tiny holes in it. It's not much, right? It really isn't much, but it's actually really, really cool that you can see, and I can't see this with the naked eye. They're so small, and I will take my safety pin and for scale, I'll show you just how small these holes are. Oops. Yeah, it's like the head of the pin. That is how small each of these are. How small some of these are over here. So unless you're looking at it with some loops or a microscope, you're probably not going to see them. Especially if this thing is not in a cut and polished state. They would just appear to be little a little pit or something at the most. So it's only when you cut it open that you can find stuff like this. So that was our last eucrite. So now we have some diogenites. So let's look what the diogenites look like. So this one is Tatahuine. Tatahuine. Yep, Tatahuine. So this, there we go. Tatahuine. It's a diogenite from Tunisia in 1931. This one was found. So this, do you see that green color? That green color, that's an indication of olivine. So I wonder if this is an olivine-rich diogenite from the lower mantle. I'm not 100% positive. I can always look it up fairly quickly, but it's entirely possible. But here we go. So this material is so unique because it comes from the mantle of an asteroid. This is the only material that we've ever found from a mantle. Not this particular material, not this particular meteorite, but the diogenites. So if you think about it, we have not been able to reach the mantle of our own planet. It's right underneath our feet, but it is so technologically difficult to get down there that we are still like at our deepest point. We are still kilometers away from reaching the MOHO, the boundary layer between the crust and the mantle. So we don't have any raw mantle material available. We have stuff like the Hawaiian basalts, but that's not quite really pristine mantle material like this is. So like the Hawaiian hotspot is pushing up material from the mantle through the crust and into the volcano. So we're getting mantle material, but it's not pristine. So, and it's not deep. This is all shallow mantle material. So in this case, what we're seeing is deep, solidified mantle material from an asteroid. So just think about it. This particular rock was under the surface of Vesta, 100 kilometers or more, probably more, about 200 or probably about 200 kilometers under the surface of Vesta. Here's the raw, the other side, because this is an end cut. Yeah. So we can see, yeah, it's not even that interesting. It really isn't that interesting on that side. It's just rough, and it's hard to see anything on there anyway. Let's try this again. Let's get a better focus on it. So I don't know if you were expecting to see mantle material from an asteroid today, but here you go. This is mantle material from the asteroid 4 Vesta. It's fairly uniform. There's that, I can't even call that a crack. It's a vein of material. I don't know what it is. But that's pretty cool. Mantle material from an asteroid. We have another diogenite, and this one is Northwest Africa, 12739. Northwest Africa, 2739 diogenite. And this is more shallow mantle material. It doesn't look like, it kind of looks like the howardite. It kind of looks like the howardite in that there's, excuse me, little bits and pieces through here. And they're also broken up, little inclusions. But the background material is completely different. The matrix that's holding it together is much, much darker. And it doesn't have that green color to it. So this is not olivine rich. So this looks like it's a mixture of crust and mantle, a little bit of crustal material, but it's those rocks suspended in molten basalt and molten mantle material. If you look at this, This is nothing like what we previously saw in the deeper olivine-rich diagonite, which is really, really uniform. This one, it's broken up pieces in a darker matrix. So it looks different than the crustal material, than the howardite. And there's no iron in here. If I take the magnet to it, take the magnet. So we have bits and pieces of iron in the howardite. So that's understandable because the crust, the surface, is being impacted by other asteroids. They get pulled in by the gravity of Vesta, and they impact on the surface and break apart. So if you have an iron asteroid or meteoroid that's going to impact the surface of Vesta, get blasted apart, it's going to blast little pieces of iron everywhere. That'll get incorporated into the crust, and for millions of years to get solidified. That doesn't happen down in the mantle. In the mantle, it's molten material. So I'm moving. There's no iron in this. I'm getting nothing. There's no shininess to it. There's like a little shiny bit right here. No. Not the shiny bit? Oh, there's this part. Yeah. That's the shiniest bit right there. Yeah. It's the shiniest little bit right here. Oh, so it's a bit lower. Push this up. So where's that little bit right there is kind of shiny from one angle. That's not iron. There's just no iron in here. Sharper. There we go. That's a bit sharper. Yeah. Even that little bit right there, that there's just no iron in there. That's something. That's a little bitty crystal that I can see. So yeah, all the iron went down into the core. So the mantle doesn't contain any iron. Because it's liquid and the iron's heavier, iron is going to drop down into the core. We might find some nickel iron on the crust only because of impacts from other asteroids or meteoroids. The mantle is not going to have iron in it, and so we don't find any iron in this. But because it was melted, we don't see any chondrules. We see bits and pieces of stuff. We see some stuff which is rounded off, like this little black fleck here in the middle, right there. That's a little bit rounded off. Some of these are more rounded than others, so it could be from melting. Some of them are not. That black one's fairly angular. That one's fairly angular too. We have angular pieces. We have some slightly rounder pieces. But again, so this is upper mantle material from the asteroid Vesta. Is that cool? I think it's pretty cool. All right, so we've gone over the head group. We've gone over, we have howardites, we have eucrites, and we have diogenites. So we're able to see various types of rocks coming from asteroids. Let's see, what else do we have here? Primitive chondrites. Oh, so I have everything kind of off in the cases, off to the side, so it's kind of just putting everything away. A lot of the stuff I have is Northwest Africa. You have a primitive chondrite. Ooh, that's actually kind of interesting. The primitive chondrites. Another primitive chondrite. We have a couple primitive chondrites. That's kind of cool. All right, so here's what we're gonna do next. We're gonna look at Tinduf. I forgot that one. Deerhurt and Tinduf, huh? So here's one from Algeria. So this is an H6 chondrite. And H6, there's H and L and LL. They're just different types, and it just depends on what's on the inside. Let's go back to the microscope. This one's Tinduf from 1997. I can't even tell this is a chondrite. I can see the iron in it, but I guess this one's just hard to. I don't know. I don't see any chondrules. Oh, there we go. There's that kind of roundish shape right there in the middle. Could quite easily be a chondrule. This is just so dark that I don't even know what to do with it. But you can see the little flecks of iron in there. They're kind of rusted out. We see the surface. Jeez. All right, that's Tindouf. That's your fairly famous one. Tindouf, an 8-6 chondrite from Algeria, 1997. I really haven't been looking at it too closely, but we have some primitive chondrites. So primitive chondrites are really, really old ones. And yeah, again, all the iron's kind of rusted out. L3 primitive chondrite. You know what? Let's get away from the primitive chondrites. I want to go to something a little bit more interesting. I don't have those two, and they're just not terribly interesting. Instead, we're going to do this. Let's start off with something really cool. Northwest Africa, 12965. Northwest Africa, 12965. That's actually a really pretty rock. I think this one's really, really pretty. This one is Northwest Africa, 12965. This is a Mars Shergotite found in 2019. This is a Mars rock. It's called Shergotite because the first rock that fell in Australia near the town or geological feature called, I believe it, Shergotite or something like that. Not Shergotite. Shergotite is a rock. So Shergot, I think, is the name of the location. But that was the first sample, and it was suspected to be a Mars rock until we actually sent probes to Mars. When we sent probes to Mars, what did we do? We were able to analyze the rocks. We were able to analyze the atmosphere of Mars, which is the important thing. So on Earth, we can take these rocks and we can actually analyze the gases trapped inside. And if we're on Mars, we can actually analyze the gases right there in the atmosphere. And they match in the proportion of the elements to each other. So we know that the gases that are trapped in these rocks are the same as the gases in the Martian atmosphere. So these are Mars rocks. This is the only Shergotite. There are a lot of them, but this group of rocks, this type of rock, is called a Shergotite. So it's really neat. It is a piece of Mars. Something hit Mars hard enough to knock off big chunks of it that went around and around the solar system for could be millions of years until eventually this landed in Northwest Africa in the Sahara Desert. And someone found it, realized, hey, it's a meteorite. And from that, someone else bought it off of them and then cut it open and saw it and realized, you know what? This is something special. I think this is Martian, but I don't know for sure. So they sent it off to a lab, got it analyzed, and it came back as, yes, there's a high probability, 99.99, whatever, however many sigmas, that this is a Mars Shergotite. And then it gets classified, it gets an official name, which is Northwest Africa 21965. And that's what it's officially known as, and it is marked as a Mars Shergotite. So this is actually a rock Mars. And I don't know enough about it. I just don't know enough to tell you what are the minerals inside. I can tell you that there's no iron in this thing. There's no iron in there. It's not sticking. It's not doing anything. even that little bitty rusty patch where it looks like a rusty patch, I'm getting nothing out of it. Yeah, it's just not. There's just no iron in this, which is what we expect from surface rocks on Mars. Just no free iron on there. But this is still a Mars rock. So again, Northwest Africa, 12965. And actually, if you want to learn about any of these rocks, all you have to do is go into Google and type in NWA and whatever the number is, or Tierhert meteorite, Tinduf meteorite, any one of these. You can go ahead and just Google it. Seriously, just Google it. It will tell you. There's actually a website specifically for it. And let's see. So if I do NWA, let's just do NWA 12965, 12965. So you go to, it is ip.usra.edu, with the meteoritical bulletin, and it's got the entry for it. This was found in Morocco in 2019, and single stone with a fusion crust. So igneous rock with sub-ophitic texture, typical grain size, blah blah blah. Main minerals are strongly zoned pyroxene and macallanite. Pyroxene has low bake contacts with plagioclase. Opaque minerals are iron oxides and pyrrhotite. Okay, so there we go. Classification, Martian sugartite. And who has the main mass? Yes, Fabian Kuntz. So Fabian Kuntz is a dealer I've worked with. He is up in the Shetland Islands. He's a really neat guy, and so he has the main mass of it, and he's the one who actually had it analyzed, and he's cutting it up and sells little pieces of it. So and it's kind of funny. I was talking with I believe it was Marcin Chimwa in Poland, and no, I was actually talking with my dealer in Canada, Ray, and I asked specifically about cutting up meteorites because I asked, well, I've got these meteorites and I really really like them, and I like them whole. I like them like this, so I have them in my hand, and so I can show people this is what a meteorite looks like, raw. You know, if you find it out in nature and it hasn't weathered, this is what it looks like. And I said, I don't really want to cut it open. It'd be neat to see what's on the inside, but then I lose it as being a whole meteorite. And what he said was, I've never lost money on a cut meteorite. And what he means by that is when you cut it open to see what's on the inside, if you cut it in half, polish up the inside really nice, the two halves that you have are now worth more than just one whole rock. And if you cut it into a bunch of little bitty slices and you polish them so it looks really nice, you make a whole lot more money out of those little bitty slices than you would out of selling just the one big rock. And it's not just that. If you have a really expensive rock, let's say you have a moon rock. So let's say you find a 1 kilo moon rock, like this one. Slide this one under and go to the microscope. Here we go. Now focus. It's always going to be in the wrong direction. Hey, I got it right this time. Okay. You know what? We got to go out. This is a small one, but a good one. Always in the wrong direction. Okay. Here we go. This is Northwest Africa. Oh shoot! I forget. 11421. Northwest Africa 11421. out of Tindouf, Algeria. Okay. So we have a Tindouf meteorite somewhere. I have a Tindouf here somewhere. But then we also have this Northwest Africa that was found near Tindouf. So this was found by two Polish meteorite hunters, Tomasz Jakubowski and Marcin Chimois. And this is the original rock was 914 grams. So you have a 914 gram meteorite, almost a kilo, not quite. And at the time, I think moon rocks were going for, I think it's between 300 and 500 a gram. So you have a big old rock like this, at the lower end. So the lower end, it would be what, almost like 300,000, not quite 300,000 to $500,000 for this one rock. Right? I don't know about you, I don't have that kind of pocket change. And most people don't. Most institutions don't have that kind of money just to buy a single rock. So just the fact that that much lunar material enters the market drops the price down for everybody. So you can't sell it for that much because no one's going to buy it. And if no one buys it, then it's not going to be worth that much. It's not really worth anything until somebody buys it. So if you have I guess we're getting into the economics of meteorites now. If you find a meteorite, let's say, let's go back to the late 90s, early 2000s to the start of the meteorite craze in Northwest Africa. So what you had is people who started to realize that the Sahara is a great place to find meteorites. And they would go out there and start looking. Well, they realized that there are a bunch of people who live there, who actually are there all the time, and that actually cross the Sahara. So there are Bedouins that cross the Sahara on old trade routes. That's what Timbuktu is. It's a city on a major trade route going through the desert. So there were meteorite hunters that and actually dealers in Morocco that figured out that if they go to the Bedouins and other people who move across the desert, drive either on camels or in cars or in Toyota Hiluxes, if you tell them, I will give you this rock, this meteorite, find stuff that looks like this and bring it back with you, and I will pay you for it. And so they would pay them, let's say a 25 cents per gram. Say that's not even wholesale. That's to the people who find it. I'll pay you 25 cents a gram. 25 cents a gram for any rocks that you find that are like this. Okay? If it's a meteorite, I'll pay you. If not, and I'll just toss it by the side. I'm not going to pay you for anything that's not meteorite. So just be careful. Don't bring me any old rocks. So let's say these Bedouins brought back, as they were going across, they were looking, oh, I see a black rock that doesn't belong. It looks similar to this rock that the guy gave me. I'm going to take it, just put it in my bag, and keep going. When they come back, sell the bag, that gets weighed out, meteorites get sorted, then it gets weighed, and let's say it's, I don't know, let's say it picks up 100 kilos. So 25 cents a gram, or less, maybe 10 cents a gram. But whatever it is, it's going to be a decent amount of money. And it's supplemental cash. All that they have to do is look around and pick up rocks. So the dealer then gets it. Let's say he buys it for 25 cents a gram. The dealer then sorts it, gets the nicer pieces. Nicer pieces may go for $1 a gram. Wholesale prices on regular stuff, 50 cents a gram. So the guy's already made a decent amount of money just sorting some rocks. So he sells the rocks at, let's say 50 cents to $1 a gram. Those then go out to secondary dealers, collectors, people like that. They're the ones who are going to analyze it. They're going to cut it. And they're going to realize, well, this thing that I bought for $1 a gram, this is actually a Mars rock. So, which at one point was going for $1,000 a gram. So once they paid the money to get it analyzed, figured out, now it's $1,000 a gram. And again, no one can really, or very few places can afford to spend, $1,000 a gram on a big rock. And so it gets cut up into much, much smaller pieces. And now different institutions, different collectors can each have their own piece, and they can do their own research analysis on their one piece, and they don't have to break the bank to do it. And now everyone's got a sample of this one as opposed to just a couple people. Well, this one, Northwest Africa, 11421, this is a moon rock. So this was discovered by these two guys in Poland, Tomas and Marcin, on one of their trips to Algeria to do meteorite hunting. And they thought it was very interesting. They were highly suspicious. This was a moon rock from the very beginning, just because of the look of it. It was non-magnetic. There isn't any iron in here because there's just nothing. You have this one really big clast here. You have some smaller clasts, and then you have this dark gray cement. You have that black clast right there. It got it was sent away to a university in Germany that specializes in meteorite analysis, and it came back as a what is it? It is a lunar feldspathic breccia, achondrite, and this was achondrite lunar feldspathic breccia, shock moderate, weathering very low, out of Erfurt, Morocco in 2017. So this piece is the one that I take out to appreciate. This is the one that I go and say, I specifically like it when there are little kids around, because you can take this, I like to put it in a little child's hand. I tell their parents, get your phone ready. And I ask the child, do you know where this rock is from? And no, they don't know where it's from. And I say, this is from the moon. This is a rock from the moon. And they get a big old smile on their face. And that's when their parents take a picture of their child holding a piece of the moon in their hand. And a lot of people have held this in the before times. Very few have held it in the year and a half, in the past year and a half. So I think it's really, I think this is really important that we can do things like this that show people not just regular meteorites, but interesting things like this, like an actual moon rock that they can hold in their hand. And it looks like a piece of gravel. It really does, but it's not. The materials of this, we don't have a match for this on Earth, not exactly. But this does match what the Apollo astronauts brought back from the moon in terms of composition. So that's why this was categorized as lunar with very high confidence. Back down. There we go. That you have these white clasts throughout and this dark matrix material that's binding it together. So this is like an interior piece. This doesn't have any fusion crust on it. It's not an end piece, but it's really neat looking. It's very pretty. I like it, and it's 2.02 grams, so it's not very big. This is my first lunar rock. I don't have anything bigger than this, and it's just a neat little rock. And I'm really happy I can actually take this thing out and use it for outreach purposes. Or I could. You're saying present tense when it was in the past tense, and hopefully will again soon be in the future tense. Again, it's a neat little rock. It has its own history behind it. So this was at one point lunar highland material. This isn't basaltic, so this was in the highlands. This was in the, if you look at the moon, you have the dark maria, which are the basalts, and then you have the lighter colored mountains and plateaus, which are the silicates. So this is highland silicate material, And this comes from one of the craters on the moon, where something hit the moon hard enough to knock off a big enough chunk that, and moving fast enough that it left the moon's gravity and went around and around and around between the Earth and the moon for who knows how long. It could have been hundreds of years, it could have been thousands, it could have even been millions of years. And eventually, it landed in Algeria or Morocco. Was it Morocco? No, I can't remember. No, it was Algeria. Now it says Morocco. All right, it's late. I haven't gotten much sleep, so I don't remember. In this case, though, it's yeah, it's still interesting. So when we do start up with in-person events where I am able to show the meteorites, this is usually the kind of the highlight for everyone is to hold an actual moon rock in their hands. So I think it looks like a piece of gravel, but I think it's really pretty. It tells a story, and the story is that something hit the moon hard enough to knock this off, went around and around and around until eventually landed in Northwest Africa. And two Polish guys were out in the desert, and they happened to see it and thought it was special and took it with them. And once they got analyzed, they realized just how special it actually was. So I've got a bunch of others that we could go. And the question is, does anyone really want to? We've got some people on here still. So if you have any questions, now is a really good time to ask. If you have any comments, if you have any meteorites yourself, you collect them. Something that I did do beforehand. So again, in the before times, one of my dealers actually up in Canada, he sent me bits and pieces of meteorites. So here is one, actually. And this one, I think this might be actually a mesosiderite. So I've kind of been saving this one because I don't know for certain. Because this one's got a lot of iron in it. And it's this weirdly shaped iron. There's quite a bit of it. So we talk about the pallasites. The pallasites are mix of there's the stony irons. It's a mix of iron and stone. It's stone, the paracrystals, in a iron matrix. Then we have what are called mesositerites. And I'm trying to find where is my mesosiderite. There you go. Yep. That's it right there. So I have another mesosiderite, and this one, push it aside. Look at all that iron in there. So this is a stony iron where it's iron surrounded by stone. And the stony irons, we think it's a iron asteroid that smashed into a stony asteroid hard enough that the iron shattered and became embedded and mixed with the stony material. So the pallasites, it's the intermingling at the boundary between mantle and core. Mesositerites, an iron rock and a stony rock smashing each other really, really hard and becoming one. So totally different type of formation, even though we use the same designation for both. So this particular rock is called Vaca Muerte, dead cow. From Chile in 1861 is when this was found. And Vaca Muerte is the geological feature in Chile. I think it's in the Atacama Desert. I don't remember exactly, but this was actually a fairly large rock that broke up in the atmosphere and it scattered over a large area. So there's lots of examples of Vaca Muerte. It's not a single rock, it's quite a bit of it. So this is just one sample, but you can see all this iron just all through. It's just a just a lot of iron. Oops, wrong one. This is the right cover for this one. And then if we go back to this little sample here, actually, I guess this is still a chondrite, but I don't see, you see many chondrules in here. You see iron. I guess we can have a couple. I can zoom in more. What happens if I zoom in? Not exactly the best made microscope, or hey, $20 is $20, right? Yeah, I think it's the angle of this thing, and it's so polished that it's really hard to see anything but the iron. And if I flip it over, oh, we got little flecks of iron right there on the surface. So this is a weathered. You can see the weathering on it. Someone cut it right there. They just ran it against the polisher just to see what the inside looked like, and they saw the flecks of iron right there. So my dealer sent me a bunch of little bitty pieces of meteorites. So when a meteorite gets cut, when it's cut and polished, sometimes you have like little bits that fall off, and it's still meteoritic material. It's just not a whole meteorite. It's a chip. Okay, so those chips, they're not really worth anything on the market. It's like you really can't sell them because it's not finely polished. It's not cut. It's just like it's a little bit that fell off. But they're still neat to have. And so what I was doing is actually giving these away during club meetings. We would have it in the before times again. We'd have raffles, and so I just had a bunch of these, and I would put in 3 or 4 a meeting, and we would raffle those off. So over time, a great many of our club members at the Fort Worth Astronomical Societies who have their own little bitty bits of meteorites in little cases like this that they got. So to me, it's just spreading the love. I think these are interesting. I think they're not just to collect. It's not the collection part that interests me. It's the story that each of these rocks have. And every single one of these rocks has a different story. They all come from different sources. They all come from different places. Each of them has something to say. I have, got one right here. This. I have this one right here. And this is a little piece of a meteorite called Chelyabinsk. In 2013, this was part of an asteroid that exploded over Siberia, over the town of Chelyabinsk, and rained down bigger pieces and smaller pieces like this little bit of gravel. So this one, hang on. There we go. So this little piece of gravel, this little piece of gravel were found by Russians who were looking for pieces of this in the days after in the ice and snow. And when you see a little black rock sitting on top of the ice or sitting on top of the snow, it doesn't look like it belongs. And so a lot of them were easily found just because they stood out this way. So one guy who found them, who found several, was also a woodworker. And he made these little meteor fridge magnets. They have this one has a little magnet on the back, and it'll just go in your refrigerator. But it's a little flaming meteor with a real piece of Chelyabinsk glued on the front of it. And my dealer in Canada sent me down one of these because he had gotten a couple from this guy in Russia, and he thought it was really neat. This is a piece of folk art. I mean, this is literally folk art. It is handmade. It's handmade by some guy out near Chelyabinsk, and doing it out of his house, hand carving it is what it looks like, hand painting it, and making a little piece of art out of stuff that he's got lying around. And it just so happens that a little piece of it is is a little piece of an asteroid that burned up in the atmosphere um, over his hometown. So it's really neat, and I like it. It is not on my refrigerator because I have a 5 year old, and if it was on the fridge, it would get lost. So I don't want that to happen. So this stays in the outreach box, and it's just a neat little piece that you can show off of genuine folk art. And the other piece of Chelyabinsk, let's see, let's go to the microscope. There we go. So this is fairly, this is unweathered fusion crust, and you can see what it looks like. It's melty. It's kind of blobby. It's there are places where it looks kind of there's like a string right here. Let's see. I gotta get the pin to move it. So, oh, I want to stab myself, but I gotta pick up the safety pin. All right, see, where is it? Oh, that little bitty stringiness right there. Or is that? Oh, never mind. That's a hair. That's just a hair. Hair that's stuck to it. So you have this little blobbiness here, kind of. That's the only word I can think of to describe. It's kind of little blobs. But this is the fusion crust, and it's very, very thin. If we look over the rest of it, this part right there is apparently where some of the fusion crust broke off. So either it could have hit the ground, it could have hit a street or something, chipped off a little bit of the outside, and that's what's left. So we can see the inside, and the inside is this light color. And if you actually Google cut pieces of Chelyabinsk, it is this light color. The outside is always, on meteorites, is always going to be black like this. But the inside something else. So light colored inside. I wonder if I can zoom in. Can we get it? How much closer can we get it? That's why I need to modify this microscope. There we go. So we can see super, super thin fusion crust. It's just very, very thin. And then we can see the inside. Here we go. Maybe. The inside. A little better focus. Totally different. And it's not polished, so we can't really see any chondrites. This is an LL6, LL5 chondrite. Can't really see them because, again, it's not cut, it's not polished, so there's not a whole lot of definition between chondrites and between the surrounding matrix. It's just really hard to see. But the fusion crust is neat because we can see, once I focus, yeah. We can see what a fresh fusion crust actually looks like. And it's very, very dark. It looks melty. If I look on the other side, oh, that's even better. So you can see the differences. This may be partially oriented. It's really hard to say. It's really hard to say with this one. This one may not have tumbled very much because if you look at the fusion crust on this side compared to the other side and compared to the edges here, the stuff in the middle is like barely touched. It's a little bit, but it's not as strongly like burnt caramelly looking. That's a word. Burnt caramelly. So what this means is that when it came off of the main mass, it didn't tumble. It didn't roll. Instead, it may have just like it was oriented. So it just broke away and just kind of may have rotated in one direction. Like if it was coming down this direction, it may have rotated like this or it may have tumbled a little bit like this, but it didn't rotate around so that all sides had equal time exposed uh, to the rushing in air. So we do have some fusion crust on it, but on this side there's just not a lot. And it doesn't look like it was scraped away. It just doesn't look like it was scraped away because there's no tool marks on here. We don't see any scratches. Um, you can't really chip it away without because it's so super thin. There's not a way that you can like chip it away easily. And there's no tool marks on here. And also you see this like little X shape or T shape right in the middle. Um, yeah, it doesn't look like it. It looks like it was partially oriented to me. It doesn't look and really I haven't taken this close of notice before, but it doesn't. Yeah, that's the way to describe it. It looks like it's partially oriented. It didn't tumble around to get equal access all around to the uh, oh, to the um, to the air. There we go. But very neat, and I really like the Russian folk art. And I think that should do it. I don't really. I've got a lot of others, but really, it's now 10 o'clock. Um, it was about 3 hours. We've gone through quite a few meteorites and talked about them. Specifically, I really wanted to go over the head group, the Vesta, the four Vesta meteorites. I'll talk about a little bit about the stories that meteorites can tell us, why they're important. They really tell us the story of the solar system. It tells the history of the worlds that these rocks come from. Um, every meteorite is basically a free sample return mission. It's just a random sample you're dealing with. So you don't get a choice in what you get with a random meteorite. Um, you get what you get, and you like what you get. And hopefully you get lucky and you get a Mars rock, or you get a Vesta rock, or you get a moon rock. Um, we may have one, maybe, we have one possible Mercury meteorite. We have no Venus meteorites. And we don't think it's possible to have any Venus meteorites because of the gravity on Venus and because of the thick atmosphere. Obviously, no meteorites from Jupiter, Saturn, Uranus, or Neptune because they're gas giants. And definitely no meteorites from Pluto because it is way far away. And it is highly, highly unlikely that we would ever get any. Do we have any extrasolar meteorites? I don't believe we have any confirmed extrasolar meteorites. I could not find any. We had that one, was it Omero? The probable extrasolar asteroid that came through. Um, but as far as extrasolar meteorites, I don't think we've ever found any. And again, the way we would analyze it is uh, we would look at, if it was a chondrite, we'd look at the chondrules and we would analyze their composition and compare it to chondrules from every other meteorite, compare them to the atmosphere of the sun and see what that looks like. So far, I don't think we've found any. I may be wrong. I'm totally open to being wrong. I would love to get my hands on a extrasolar meteorite. That'd be pretty cool. A meteorite from another world outside of our solar system. Um, I don't think we have any. So I don't see any other questions in the chat. It's been kind of a quiet stream today, which is still absolutely fine. I'm going to check the weather, see what the weather's like this weekend. May do a star party on Saturday if the weather clears up. So far, it's looking kind of iffy. I'll know more tomorrow and plan accordingly. But yeah, again, I don't see any questions, so I'm going to go ahead and call tonight. Thank you very much for joining us. I'm Chris Moynitsky, again with the Fort Worth Astronomical Society. So thank you for joining us, and good night.